Let us begin. We're going to be looking at a problem from section 5.1 on vectors, specifically in this case, three force vectors acting on a single ring. This is problem 64 on page 145. I encourage you, before watching this video and the explanation that accompanies this video, you attempt to solve the problem yourself. So here's our ring. We have three forces that I labeled as F1, F2, and F3. Our question is, what is the net force that must be acting on this ring? To make this assessment of net force, what we'll need to do is look at the forces in the x dimension, in the y dimension, add up all the components of each of these vectors to get to the resultant vector of these three forces. That resultant vector, or the sum of these three vectors, is the net force. So our net force is going to be the sum of all the forces, right? Net force, sum of the forces, same idea. And we know that's going to be F1 plus F2 plus F3. Analytically, how we can add these three vectors together is by their components. So if we say, I'll put it under the diagram here. So we'll say forces in x, and then forces in y, and then we'll also look at each of our force vectors. First, the first vector. The first vector, force 1, on the ring is pulling directly to the left, which we'll call this direction west. Call this direction east, and then up north and down south. So we have in the x direction 128 newtons to the west, or in the negative x direction. So negative 128 newtons. There is no component of this force that acts in the up and down or y dimension. So it's 0 newtons in the y dimension. We consider the second force. This time we have a force going to the right, or in the positive direction, 64 newtons. But still, there is not a component or a part of this force vector that is in the y dimension, so 0 newtons. Our situation becomes a bit trickier whenever we look at force 3, because now we have a vector. Now we have a vector, force vector, that is not just along the x or just along the y. It's a little bit in x, a little bit in y. We can look at this vector alone. If I draw this vector here, here's force vector 3. This can be split up into two component vectors. Here's force vector 3 in the x dimension. There's force vector 3 in the y dimension. And we have an angle here of 30 degrees. We have the magnitude of this force vector at 128 newtons. Using our trigonometry, our trigonometric functions, we can relate the magnitude of this force, in this case from a triangle perspective, the hypotenuse, to both of the component vectors that we need to find, and relate them through the angle. To find first the x dimension, or the x component of force 3, we'll need to relate two of the things in this triangle that we know to that third thing we want to know. That third thing that we want to know right now is the x component of force 3. So we have the adjacent side to this angle and the hypotenuse. An adjacent and a hypotenuse side with an angle, that's cosine. So I know that the cosine of 30 degrees is equal to the adjacent side, so the force in the x component of the third force, that adjacent side, and then the 128 newtons is my hypotenuse. Rearranging this equation, multiplying by 128 newtons, and the cosine of 30 degrees isolates our x component of the third force. So if we take 128 times the cosine of 30 degrees, we get 111 newtons. 111 newtons to the right. 111 newtons, and that is to the right and in our positive direction. 111 newtons. Now we'll go through that same procedure where we take one or two knowns and relate them to our third unknown. In this case, our unknown is now the y dimension. So that's the y component of this vector. Instead of using cosine this time, we'll be able to use sine. So if we take the sine of 30 degrees, that is the opposite side, which in our case right now is the y component of the third force vector, divided by the hypotenuse, 128 again. Doing similar rearrangement here, we see that 128 newtons times the sine of 30 degrees will give us the y component of the third force vector. 128 times the sine of 30 degrees is 64 newtons. Upwards, right, in the positive direction, positive y, or to the north. So we get positive 64 newtons filled out right here. Now to find our resultant vector, which we know that the resultant vector is our net force, right? Whenever we add these vectors together, that's the same as our resultant vector, which in our case, adding all forces together, that's the net force, right? In order to do that, analytically, we just need to add these components downwards. Of course, on our right-hand side, all we have left is 0 plus positive 64, so we end up with positive 64 as the resultant's y component, or the net force's y component. In the x dimension, we have negative 128 plus 64, and then plus 111 newtons, resulting in positive 47 newtons. That tells us that the resultant vector here in this case, and therefore the net force that's acting on our ring here, is 47 newtons to the right and 64 newtons upwards. What might that look like? Let's draw that. I'm not going to draw it back on our diagram up here on the top left, but I'll draw it just below. Well, positive x is to the right, positive y is up. So it's to the right and up by something like this. Okay, there's our to the right and up, where we could say here this bottom, because it's in two dimensions, can be split into two components. Or because it's not just to the right or just up and down, then it can be split into two components. This is our net force. This is our net force in the x dimension. This is our net force in the y dimension. We know that this is the magnitude of this is 64 newtons. The magnitude of our x component of the net force is 47 newtons. So that's what our analysis here in this table demonstrated to us. Now our question is to find what is the net force. We found the components of the net force, but we have not yet found the actual net force. Remember, force is a vector. So when we say find the net force, that means we need to find both the magnitude and the direction. That means we need to find the magnitude of this net force. In this case, in this triangle's case, the hypotenuse, which we can use a squared plus b squared equals c squared, the Pythagorean theorem. Our a, maybe we'll treat as this side down here, the x component, is 47 newtons. 47 newtons squared plus 64 newtons squared. The square root of that sum should get us what c is. The square of 47 plus the square of 64 and the square root of that sum is 79.4. We'll hold on to only two significant figures here. So 79 newtons. That is the magnitude of this force. So we found the magnitude of the net force. Now we need to find the direction of the net force. That means the angle, right? This theta, whatever that is there. Now we know the opposite side of this triangle and the adjacent side. If we use arc tangent or the inverse of tangent, so I can say tangent inverse of our opposite, so 64 newtons over our adjacent, 47 newtons, which is the same thing as saying the arc tangent of 64 newtons over 47 newtons. Then I'll find what theta is. I'll find out what the degrees of that, the angle associated with this triangle, which therefore would give me the direction of our net force. We find that it is 53 degrees. 53.7, so I have 54 degrees. Here is our direction. And right above it at positive 79 newtons, or 79 newtons, we don't need the positive or negative because this is just the magnitude, and the direction gives us, so I'm actually going to remove that positive. The direction is given by these 54 degrees. We have now found the net force that is acting on this ring given these three forces. All right, thank you.